Very good afternoon, everyone. Thank you all for joining us today. I sincerely appreciate your participation in this session of our faculty interaction webinar series titled Sensing Property of Group VF Monolayer to Volatile Organic Compound based on the first principle investigation using the Synopsys QuantumATK software. So it is my pleasure to introduce our esteemed speaker for today's session, Dr. R. Chandiramouli. So Dr. Chandiramouli is currently a senior assistant professor in the Department of Electrical and Electronics Engineering at the SASTRA deemed University, Tamil Nadu. So he has made remarkable contribution to the areas such as nanomaterials and their applications, 2D materials, molecular electronics, and nanosensor. His research is deeply rooted in the advanced computational methods that pushing the frontier of material science and device application. So with a strong foundation in the theoretical and computational physics, Dr. Chandiramouli has extensively explored the electrical, electronics, magnetic, and thermal property of nanomaterials. His work also encompasses materials and device modelings. So in today's session, Dr. Chandiramouli will share his research insight on leveraging the Synopsys QuantumATK software to investigate the gas sensing capability of the monolayer materials. His presentation will emphasize how atomic scale modeling and simulation can propel innovation in this rapidly evolving field. So following the talk, we will have a live demonstration by the Dr. Nagarajan. So he's currently an assistant professor in the same department at the SASTRA University. So he'll provide a hands-on walkthrough of the Synopsys QuantumATK software, showcasing its practical application in the studying gas sensor mechanism of the monolayer materials. So with this brief introduction, I would like to hand over the session to our esteemed speaker, Dr. Chandiramouli. Over to you, sir.
Good evening to one and all. I am Dr. R. Chandiramouli from SASTRA deemed University. Today I am going to give the talk. The topic is sensing properties of group 5A monolayer towards volatile organic compounds based on a first principle investigation using Synopsys QuantumATK software. So after my presentation, my colleague Dr. V. Nagarajan from SASTRA deemed University will make a demonstration how to construct the chemical nanosensor and how to conduct the material property studies, etc. So first of all, I would like to thank Integrated Microsystem IMS for arranging this webinar, and particularly I thank Mr. Deepak Upadhyaya for facilitating this webinar. Now we will start for go into the presentation. So the outline of the presentation, it includes the QuantumATK software features. What are the features involved in the QuantumATK? And then we will discuss some of the properties of two-dimensional material after the emergence of graphene. And we will also discuss about the advantages and applications of 2D material in day-to-day life. And also the outlook of QuantumATK for chemical nanosensor, how to study the material property and also the device design for the chemical nanosensor. And also we will have a discussion on the comparison of QuantumATK with other packages such as VASP and SASTRA. And we will discuss some of the material property which can be studied based on the QuantumATK package. So first of all, we will have a glimpse on the QuantumATK software features. Why we go for a QuantumATK package? So the system configuration, the QuantumATK system configuration supports from 0D to 3D material. So 0D material such as molecules, polymers, etc. And also we can go with the clusters and the 1D materials such as nano tube and nano ribbon, and also the 2D materials such as a nano sheet that can be simulated. Apart from the 0D, 1D and 2D material, we can also go for a 3D material such as the crystals and amorphous material. Furthermore, we can also go with the interfaces and multi-layer structures. And particularly the QuantumATK software, it supports the device design. That is very, very important one. So whereas the other package that will not support the device design. So except the SASTRA and the nanodecal, so the other packages will not support the device design. And what is there in the QuantumATK compared to the other packages? So the QuantumATK is having the virtual nano lab, so along with the GUI, graphical user interface, so that we can easily build the desired material. So there is a building tool so that the 1D, 2D materials and the device design can be easily built using the tool. And apart from that, there is also the inbuilt database is also there, and the calculation setup is also there. We can choose different levels of theory, such as a GGA or LDA or different basis set that can be chosen, and we can submit the job for the execution. And the different properties, optical, mechanical, and electronic properties, everything can be incorporated, and the job that will be executed by a Python scripting, and we will have the insightful analysis by using the QuantumATK package. And after getting the result, we can also visualizing tool is also inbuilt, so such as the projected density of states, band structure, electron density difference, EDD, electron localization function, ELF, everything can also be obtained by using the visualization tool. And the simulation engine, so that support the nano electronic device, so that is in the nanometric regime, starting from a 10 power minus 9 nanometer up to 10 power minus 7 nanometer dimension, that is suitable. So the QuantumATK package is suitable. Beyond that, below that of 10 power minus 7, that is if it is in the microelectronics, then we can go for a TCAD only. So after that, we will also discuss about, since the topic revolves in the group 5A material, we will discuss about the advancement of phosphorine. That is one of the group 5A material, advancement of phosphorine nanosheet material as a chemical nanosensor. And also we will discuss some of the things based on arsenic. The arsenic, which is being exfoliated to arsenic for chemical nanosensor property and applications. And we will have some discussion on the reported work from our research group, and followed by the demonstration by Dr. Nagarajan for 2D material as a chemical nanosensor application. So first we will go into the properties of a 2D material. So after the discovery of graphene in the year 2004, so researchers focus on the 2D material. Moreover, the graphene is a energy band gapless material, so that that cannot be used for chemical nanosensors unless it is doped or it is functionalized, so that the graphene is not suitable for the chemical nanosensor or a biosensor. So for that purpose, the researchers are in search of the various other two-dimensional material, so that such as the group 4A material, such as silicene, germanium is being explored, and in recent days the group 5A materials such as the phosphorine, arsenine, and antimony is also being reported, and it is also being used as a chemical nanosensor and for biosensors. So as we already know that the two-dimensional structure have the thickness in the range of 1 to 100 nanometers. And the other different properties of a 2D material is, it is well known one, that is the 2D material will have high surface to volume ratio, and also it has excellent mechanical strength and flexibility. Also that will have the good thermal and electrical conductivity. Apart from these features, these properties, it is also ultra thin and light in weight, and the significant surface area, because of her high surface to volume ratio, it is also having a significant surface area, and it is highly porous. It is also having high porosity, so that where the target gas or a vapor molecule that can be easily absorbed. The other important thing in the 2D material, important property is 2D materials are tunable for the optical properties. So the band gap can be tuned, so that the various electromagnetic spectrum, so that can be tuned for various electromagnetic spectrum, and it is also having a good electrical, electronic, and chemical properties. All can be tuned by a different means, that is by doping or functionalization. And moreover, the 2D material is also highly chemical activity. It is also having high chemical activity at the surface and the edges, so that the vapor or a gas molecule that can be easily absorbed, and it can also be used, 2D material can also be used for a filtering purpose and all, and it is also having the potential for a functionalization and modification, so that because of the edge border effect, so that if we need to fine tune, tailor the 2D material, it should be, the 2D material should be halogenized or hydrogenated at the edges, so that will also have some more additional property, and that may also be functionalized vertically, so that the band gap can be fine-tuned or band gap can be opened if it is a conducting material. And it can also, 2D material can exhibit high transparency for some of the material, and also it will have some strong adhesion to the substrate. And apart from that, it is also having unique magnetic, dielectric and catalytic property depending upon the composition which we are using it. And based on all this property, so the two-dimensional material are application specific selectivity. It is also highly selective for a particular target molecule, and it is also biocompatible. And what are the advantages and applications of a 2D material? So the advantages is the high sensitivity due to large surface area of analyte absorption because of high surface to volume ratio. So that the two-dimensional material are highly selective, highly sensitive and selective to a particular target molecules or the gas or vapors. And it is also having a rapid response. The response time that can also be minimized, and the recovery time is also being minimized depending upon the physics option. So we can also fine-tune the 2D material for its rapid response and recovery time towards the target molecules. And it is also selective detection. We can also go for selective. So if it is a air atmosphere, so apart from the target molecule or target vapor, so other gas molecules such as O2, CO2, NO2 is also present. And if you use a 2D material, so that will also be highly selective, and the selective detection of the various ions and biomolecules are also possible. And also we can functionalize the 2D material, so we can hydrogenate or halogenate, so that the functionalization enables the specific recognition of a target molecule. And the miniaturization and integration onto the flexible substrate for wearable devices is also possible when we use a 2D material. And here the real-time monitoring capability is also possible for environmental monitoring, medical, and also for industrial applications. And it is also having the ability to detect a low concentration of a vapor or the gas molecules present in the atmosphere. And it also enhances the safety and diagnostic efficiency can also be achieved in 2D material, and compatible with the electronic readouts, so that using the 2D material that can be used for a FET, field effect transistor based chemical sensor, and also chemoresistive based sensors. So whenever the adsorption and desorption process of gas and the vapors, it leads to the changes in the resistive property, that is a chemoresistive sensors. And the other advantage is it is a facial fabrication technique such as the mechanical exfoliation or a chemical exfoliation, and printing is also possible in the 2D material. So these are some of the widely used 2D material. So in the elemental form, so that we have the group 4A materials starting from graphene, silicene, or germanium, and also the group 5A material, that is the black phosphorus, red phosphorus, etc., and also arsenine, antimony, all are elemental 2D material. And also the non-metallic compounds is also there. So that is the GC3N4, graphitic carbon nitrate, and also the hexagonal boron nitrate is also there, the non-metallic compounds. And the metallic compounds such as MoS2, MoSe2, MoTe2, and alpha V2O5, vanadium pentoxide, gallium selenide, and MXenes is also there. And apart from that, the organics such as the metal organic framework, MOF, metal organic framework, and the covalent organic framework, COF, is also there. And some of the salt such as clay and CaTiO3 are some of the examples of different 2D materials. And now we will switch on to the outlook of QuantumATK for a chemical sensor. How we can deploy QuantumATK for a chemical nanosensor. And QuantumATK, that is used for the atomistic modeling. So that is in the nanometric regime. In the order of angstrom unit, QuantumATK is used for atomistic modeling and simulation of a nanosystem, including a device design, So that can be used for a chemical and a biosensors. So what methodology is used in a quantum ATK simulation? So the methodology involved is for a material property studies, you can use a density functional theory. If you go for transport property for a device fabrication, apart from the density functional theory, in combination with the non-equilibrium Green's function, NEGF, non-equilibrium Green's function, so that we can also have the transport property such as IV characteristics, etc. So to perform the first principle calculation for a electronic structure calculation and a transport property calculation. And this is crucial for modeling the electrical response for a sensing material towards the target vapors or target molecules. What are the key capabilities in the quantum ATK? So it is the simulating a electrical transport property. We can simulate electrical transport property of a nano device in the atomic scale. So that is in the order of angstrom unit or nanometer, and also we can calculate electronic properties such as a band structure, the energy band gap from the band structure, and the density of states, hybridization of a base material with the target gas vapor molecules, and also molecular energy spectra. All can be obtained by using the quantum ATK and also with the help of visualization tools. And modeling absorption of a gas vapor molecules on the sensor surface and calculating the absorption energy is also possible using the quantum ATK. And moreover, the other important thing is we can also predict different properties. So during the interaction with the gas with the base material, predicting property like a charge transfer and the transport properties such as IV characteristics and the sensitivity change with the gas absorption and the desorption process. All these things can be studied by using a quantum ATK. So these are the key capabilities of using the quantum ATK. Is a Vienna simulation
Hello. Sir, your voice is not audible.
LCAO. We use NEGF method as well in the quantum ATK.
Sir, hello. Sir, your voice is not audible. Hello.
Is the user specific, so that will be the user either the for fast calculation, for a speed calculation, LCO level of theory or a plane wave basis set that can be used according to the need for the user. So the comparison of a quantum ATK with a SASTRA, comparison of a quantum ATK with a net பண்ணுவா. Is it audible, sir?
Yes, sir. Now it is fine.
Yes, sir. Some network problem, power fluctuation here.
Okay, sir. No, sir. Okay.
So in QuantumATK, we are having the integrated platform. So that LCAO basis that is not being used, and QuantumATK workflow is specifically tailored for the device simulation. And the basis set used in the VASP, that is the projector augmented wave plane wave based set is being used, whereas in the QuantumATK it offers both the LCAO and plane wave basis set is being used, that will allow the user to choose between the rapid or the speed calculation LCAO basis set or the plane wave basis set can be used according to the user specific. And now we will compare the QuantumATK with SASTRA. SASTRA, that is a Spanish initiative for electronic simulation with thousands of atoms. That is a open source code, so that can be utilizing the localized basis set LCAO, and it is similar to the QuantumATK model. And the QuantumATK here, the important thing in QuantumATK is the GUI, graphical user interface, is also integrated one, so that will be for any GFO module and the quantum transport calculation, so that is more suitable. And the quantum transport calculation is a further development of a trans-SASTRA C, which is based on the SASTRA technology. And the key difference between more comprehensive and user-friendly platform. So since GUI tool, and the results can be easily obtained, and that will also be the Presano lab. And also it runs, the QuantumATK runs on the Python scripting engine, and that is much dedicated towards the NEGF module for transport calculation, whereas in the SASTRA is a powerful tool for electronic structure. In addition, that in the QuantumATK streamlines the process of simulating devices under a different bias condition, and also for analyzing a transport properties. And now we will go for the different material that is being studied based on QuantumATK. So we can study the electronic property. So electronic structure, we can calculate the energy band gap, whether it is a metallic one or a semiconductor one. And in density of states, we can also calculate the band gap, and also the hybridization of the base material with the different atom, the orbitals, and also the hybridization of interaction with the target vapor and the base material, and the molecular energy spectrum, charge transfer between the gas and the base material, and the molecular population analysis is also possible, and defect formation energy and thermodynamic transition level calculation is also possible. And apart from that, the effective mass calculation is also possible in the QuantumATK with regard to the material properties. And in the with regard to the transport property, by using the QuantumATK, we can use IV characteristics, current voltage characteristics, and also the absorption energy of gas molecules on the sensor surface is also possible. And we can also calculate the electrical conductivity and sensitivity, and also electron and phonon transport property is also possible with regard to the transport property. So according to the structural and the dynamic property, we can make use of a QuantumATK for a geometric optimization, and also the reaction path optimization, such as the nudged elastic band NEB method, that can also be used in the QuantumATK. And absorption and desorption energy can also be calculated, and some of the thermodynamic properties, such as reaction free energy and transition temperature, is also possible by using QuantumATK. And apart from these things, the molecular dynamics simulation is also possible using the QuantumATK. And here the important thing is the application, the deployment of a basis set. So since if you use VASP, so even though it is more accurate, so the VASP, that will be primarily using the plane wave basis set, projector augmented wave PAW basis set. However, in the QuantumATK, so the choice is based on the user specific. So that quantum ATK, we can also go with the LCAO, so which will give rise to a rapid calculation. And the plane wave based set, if you need more accuracy, we can go for a plane wave based set, allowing the user to choose between the rapid calculation, speed calculation, and or else we need accuracy means we can also go with the plane wave based set as needed by the user. So now we will discuss about the group 5A material, which is deployed for the chemical nanosensor. So as we already know from the periodic table, group 5A material, that is a phosphorus, arsenic, antimony. So these are the group 5A material. So now we will discuss with the phosphorine as a chemical sensor. So it's a property and applications. So phosphorine is exfoliated from a 3-dimensional phosphorus. So the widely known phosphorus is a black or red phosphorus is already known. And here, so when we compare with the graphene 2D material, which is having sp2 hybridization, so that because of that it is not having the energy band gap, so that it is having 0 band gap, so that cannot be used as a base material for the chemical nanosensor. However, if you use group 5A material, so because of sp3 hybridization, so the band gap can be opened. So the band gap can be opened, and so the sp3 hybridization, it gives rise to the puckered alpha or a buckled beta structure. So that this unique non-planar, so it is not a planar structure as that of the graphene. The phosphorine is a non-planar puckered honeycomb lattice. It gives a phosphorine an extremely high surface to volume ratio, which is suitable for the base material for the chemical nanosensor. And this maximizes the interaction site for the chemical analytes, which is crucial for a high sensitivity and selectivity. And the band gap can be fine-tuned. So the important feature of using the phosphorine is the band gap can be fine-tuned, so that the phosphorine band gap can be adjusted by changing its thickness, whether we use a bulk phosphorus or the few layer or a monolayer phosphorus. So depending upon that, we can fine-tune, tailor the band gap. So a monolayer band gap, so that may have a band gap of 2 electron volt, whereas if you use a bulk black phosphorus, that is having a band gap only approximately in around 0.3 electron volt. So when we exfoliate a monolayer from the bulk phosphorus, so whether it is a few layer or a monolayer, so a 0.3 electron volt black phosphorus can be fine-tuned to a very high band gap, so material such as up to 2 electron volt. So this tunability allows the fine-tuning the material's electronic property for a specific sensing application and also for optical applications. And the phosphorine, so that will also have a high carrier mobility. It exhibits a high charge carrier mobility, which enables the fast electron and hole transport. And this property gives rise to a rapid and measurable change in the electrical conductivity when it is exposed to the target gas or vapor. So that will also ensure the quick rapid sensor response. And the phosphorine also have high surface reactivity. So if it is a highly surface reactivity, so then that will be suitable for a catalyst as well as for the chemical nanosensor. So the phosphorus atom have the lone pair electron that makes the surface more reactive, and this facilitates strong absorption of a gas and chemical molecules, so which will improve the sensor's overall performance. So that is a sensor's overall sensitivity. So these are the various allotropes of phosphorine. So apart from that, the different thickness, so we can also fine tune the base material phosphorine by a different allotropes. So here we can see a number of allotropes of phosphorine starting from alpha, beta, gamma, delta. You can see that alpha is a puckered structure, and the beta is a buckled structure, and the gamma is somehow like a sawtooth structure, and the delta is also somehow related to the puckered structure. Alpha, beta, gamma, delta. So if you see that the alpha phosphorine, it possesses a direct energy band gap of 2 electron volt, and beta also have indirect. So the beta also have the same band gap around 2 electron volt, but it is indirect one. Alpha is a direct one, direct energy band gap, and the gamma and delta is having an indirect band gap of 0.5 electron volt. And apart from that, So the red phosphorine is having indirect energy band gap of 1.96 electron volt. Green phosphorine also exists with a direct band gap of 2.4 electron volt. Indirect, the other combination is alpha beta phosphorine, beta gamma phosphorine, gamma delta, gamma alpha phosphorine, alpha delta, and beta delta phosphorine is also possible. And here you can see that the majority of the allotropes, so that may be indirect energy band gap or else direct energy gap, so that we can use the direct energy gap for the optical material and also indirect energy band gap for the chemical nanosensor and the biosensors. So that depending upon the allotrope also, we can fine tune the band gap apart from the thickness of the phosphorine. Apart from that, the other allotropes of phosphorine also exist. So that is epsilon phosphorine, zeta phosphorine, eta phosphorine, theta phosphorine also exist. And alpha epsilon, beta epsilon, gamma epsilon, delta epsilon, and delta gamma phosphorine, psi phosphorine, violet phosphorine, cagone phosphorine, and porous phosphorine. Different phosphorine exist in the group 5 material, so which can be used for a various application. Then what are the applications of a phosphorine? So the main applications of phosphorine, so it involves with the gas vapor sensor. So phosphorine is highly effective in detecting the various vapor gases, not only for vapor gases and particularly for the vapors. So that is the volatile organic compounds that is suitable at a very low concentration. Even at a very low concentration, the parts per billion, so the phosphorine is suitable, and it is also suitable for biosensors because of its large surface area and its ability to be functionalized with the halogens or the hydrogenator, so making it is a promising platform for biosensing. And phosphorine can also be modified, so that can be the doped or that can be functionalized, modified to detect specific biomarkers from the exhaled breath and for detecting different types of protein and also for DNA sequencing. Now we will discuss some of the things based on the another group 5A material, that is arsenine, which is the arsenine is exfoliated from the 3-dimensional arsenic. So arsenine for chemical sensors. So what are the properties and applications? First we will discuss about the property. And arsenine is a wavy two-dimensional structure. Similar to the phosphorine, arsenine also exhibit a puckered and buckled honeycomb lattice, and it is also highly surface reactive. On the surface of the arsenine with a lone pair electron on the arsenic atom is highly reactive. So this facilitates a strong interaction. So that is a strong interaction of the target molecule, means so that will be chemisorb. So for a filtering purpose, we can make use of it, and with many gas molecule which can significantly alter the material's conductivity, and that will improve the sensing response of the base material, that is arsenine. And doping, so we can also make use of doping and functionalization to fine-tune the material. So doping to enhance the performance of arsenine. Sensing capability of a pristine pure arsenine can be significantly enhanced by a doping effect. And also, for example, if you dope with the transition metal like a titanium or a nickel, it is doped in the arsenine, so it can improve the interaction with the gas molecules, and that will also even change the electronic nature of arsenine from the semiconductor to the half metal or a conductor upon gas absorption, and that will also provide a clear and a measurable signal. And these are some of the allotropes of arsenine, similar to the phosphorine. Here also the arsenine that can be fine-tuned. We can fine-tune the band gap based on a different allotrope. So the alpha, beta. So alpha is a puckered structure, and the beta is a buckled structure, and the gamma, delta, and the T phosphorine also exist, and O phosphorine, 4,8 arsenine, and epsilon and 4,6,10 arsenine also exist as a 2-dimensional material. And other allotropes, it includes eta, theta, and HS arsenine and K arsenine. So all these different types of allotrope that is also exist for different applications. So now we will switch on our discussions to some of the reported work from our research group. So that is So we are mainly concentrating in the group 5A material, and also in some of the mixture of the group 5A and group 3A material. So this first work in this webinar is reported to the Journal of Molecular Modeling, where we explore the absorption attributes of beta phosphoborofane nanosheet towards some of the vapor emitted from the cosmetics. So the vapors, whichever is emitted from the cosmetics, that is being absorbed. So that is being sensed by the beta phosphoborofane. So here you can see that beta phosphoborofane. So beta allotrope of phosphorus, beta phosphoborofane. So phosphorine is a group 5A material, and here we used borofene. Borofene is a group 3A material, and if you use phosphoborofene, so then that will become a metallic. So we already executed that, but it is showing a metallic property. In order to make it as a semiconducting material, we hydrogenated vertically, so that the beta phosphoborofane is hydrogenated vertically, so that the band gap can be opened, so that can be suitable for the chemical nanosensor. First, we explore the structural and the electronic properties of beta phosphoborane. So first of all, we have to ensure the structural and the dynamic stability of a beta phosphoborofane. So that is confirmed with the formation energy for the static structural stability. So by the value of the formation energy of minus 4.67 electron volt per atom, so that the static the structural stability is ensured. Under the energy band gap. So the next thing is we have to calculate the energy band gap. That is very important one. The energy band gap of beta phosphoborane is 1.252 electron volt. So that it means that it is a semiconductor, so that it can be suitable for the chemical nanosensor. So here you can see the structure of a beta phosphoborane. You can see that in the vertical direction, that is the white balls, that is the hydrogen. So that the phosphorus and the boron, the borofane is being hydrogenated vertically to open the band gap. So here you can see the band structure and the PDAS spectrum obtained from the QuantumATK package, and you can see that the energy band gap at the gamma point is 1.252, and here also the PDAS spectrum, we can see that the energy band gap of 1.252, and the hybridization of a boron, hydrogen, and phosphorus atom, the sp orbital, is also been shown with a different color gradient. And here some of the vapors evolved from the cosmetics. We have chosen two target vapors. So that is hydroxycintronellal and alpha isomethyl ionic. So that is being evolved from the cosmetic. So that the absorption of hydroxycintronellal on a beta phosphorine, it exhibits a physis option. So by the weak van der Waals forces, so the absorption is by the weak van der Waals forces, it shows a physis option. So whereas the alpha isomethyl ionic, it shows a mixed physis option and a chemis option. And if it is a mixed physis option, chemis option, we have to slightly give the external energy in the form of heat energy or the optic energy to dissolve the molecules from the base material for a reusability of the base material. And if it is a physis option, it can be easily dissolved. And the absorption of the target molecule, it also leads to changes in the electronic property of a beta phosphoborofane, so including the changes in the energy band gap. So that is being observed and reported. And we also made a comparative study with the present work, that is beta phosphoborane with all other group 3A, 5A material, phosphoaluminate. So that is also being reported by our group. So where depending upon the different level of theory, we also obtained the energy gap, and the target vapor is also being listed here, and absorption energy and molecular charge transfer, that is also being reported here. And the beta phosphorine exhibit a chemoresistive nature. If you use as a two-probe device, so that it shows whenever there is an absorption desorption of the target vapor, so then the change in the resistance is noticed, so that it can exhibit a chemoresistive nature with the relative energy gap changes, indicating its potential application as sensing material for the target fragrance compound. And the concluding notes, it is overall the results demonstrate that beta phosphoborophane can be used as a sensing material to detect furan compounds, that is a hydroxycintronelal and alpha isomethyl ionine from the cosmetics. So here we use a different base material, that is a beta phosphoborophane, and the target vapor is also a new one. So that is being firstly reported, that is hydroxycintronelal and alpha isomethyl ionine. So using the QuantumATK, so we reported the new results. And also the next work is also being reported to the Journal of Molecular Liquids. So here we observed amine adsorption studies on alpha antimonate phosphorus monolayer. So here you can see that the base material comprises of two group 5A material antimony. So that is antimonate, and the another one is a phosphorus alpha antimonate phosphorus monolayer, that is being used as a base material for chemical sensor, and amine, that is a dimethylamine and a trimethylamine is the target vapor that is being explored in this work. First of all, we studied the structural stability of alpha SBP. So the optimized alpha SBP monolayer, so it shows the orthorhombic crystal structure with a lattice parameter of 3.91 angstrom, and B is 4.43 angstrom units. And the cohesive formation energy is ensured for the static structural stability minus 5.426 electron volt per atom. And for dynamic stability, we also explore the phonon band spectrum where there are no negative frequencies noticed, so which shows the dynamic stability of alpha SBP monolayer. And also the band structure and PDAS projected density of state is also being analyzed, and it shows alpha SBP monolayer has the indirect band gap of 1.013 electron volt, indicating the semiconducting nature. So this is the alpha SBP monolayer structure, and also the band structure along with the PDAS and the total density of states is also being shown. The absorption of dimethylamine and trimethylamine. So here the dimethylamine and trimethylamine that is being widely used for the studying the fish freshness. So that the TMA and DMA is evolved from the fish, as well as for when the animal is being decomposed, when the animal is dead and decomposing, and we can also have some foul smell which is due to the DMA and the TMA. So that we want to detect the DMA and the TMA presence in the fish freshness, as well as the decomposition of the animal matter, the dead animal matter. So the absorption energy of DMA and the TMA, so that is being calculated, and it is in the range of minus 0.281 electron volt to minus 0.514 electron volt. So it indicates the physisorption due to the weak van der Waals type of interaction, so that the target molecules can also be easily dissolved. And the absorption of DMA and TMA on the alpha SBP monolayer, it leads to changes in the band gap, with the maximum variation is being observed for the absorption on the top side. So here also, so we can the atomistically we can also find which site is being absorbed. So that is being a feasible absorption. So that can also be explored in the atomistic level, and Mulligan charge analysis and charge density different plot. So that is also being calculated, and the sensing response is also being found. And here in this work, in all the work, the main factor is the absorption energy, the Mulligan charge transfer, and the energy band gap, and average or relative energy band gap variation that is being explored, and that is being reported for absorption studies. And the potential application as a chemical sensor. So here this material, so that is alpha SBP, it has a quick recovery time, and of SBP, alpha SBP monolayer upon the desorption of DMA and TMA molecules suggest as a reusable chemical sensor. And the changes in the electronic property of alpha SBP monolayer, so that will indicate the suitability of a chemoresistive sensing of DMA and TMA molecules in the air atmosphere. And the next work is reported to the materials today communication. So here we are using arsine boron. Arsenic, that is a group 5A material, and boron, so boron. So that is the 2D material is a boron. So that is being we are using a group 5A and group 3A combination as a sensing material for a chlorofluorocarbon CFC. That is a freon gas. So that is for used as a coolant. So for that purpose, we have explored here also the base material as well as the target molecule, that is a dichlorofluoromethane, and the difluoromethane is the new target molecules that is being explored. So as usual, the structural stability is confirmed for the pristine arsine boron. So since these are the new materials which is being predicted by the first principle studies based on the quantum ATK, so that we are calculating the structural stability and the phonon band spectrum for the dynamic stability, and also the thermodynamic calculation is also being studied for based on ab initio molecular dynamic simulation. Also the thermal stability is ensured, and the energy band gap of arsine boron is computed to be 0.927 electron volt, which is a semiconductor. The electron state near the Fermi level of arsine boron are influenced by the p and d orbitals of arsenic atom and p orbital of boron. So you can also see the structure of arsine boron, and here you can see the ab initio molecular dynamic simulation at 300 Kelvin. So that is also being shown here, and beyond 1 picosecond, you can see that the energy almost remains same, so that beyond 1 picosecond, the material that will become stable, thermally stable. And here in the CFC, chlorofluorocarbon, so we used two target vapor. So that is a freon 2,1 and a freon 1,2. So that is being studied here, and the absorption energy is found to be in the Fischer-Tropsch regime, and the absorption of freon 2,1 and freon 1,2 on the hollow side is found to be feasible, more favorable, and relative band gap changes are also being calculated. So for freon 2,1 and freon 1,2, it is 1.62% and 12.19%, indicating the good sensing material. And these are the absorption energy, charge transfer, energy gap, relative energy gap variation. So here, with the basis set superposition error, and with and without BSE is being reported. And the other important thing is here we have also studied the selectivity. So since in the air atmosphere, so the presence of CO2, O2, NH3, and humidity H2O is also there. So we can also studied about the selectivity of freon 1,2 and freon 2,1 along with the some of the atmospheric gas. So for a selectivity, the molecular charge transfer for freon 2,1 and freon 1,2 is in the range of 0.001 E and 0.113 E, confirming the donor acceptor nature of the during the interaction, and selectivity of arsenine with the atmospheric gas molecule is also being reported. And the next work we report to the chemical physics letters. So here it is we used phosphoboron group 5A and group 3A nanosheet that is being used as a sensing element for LPG, liquid petroleum gas. So the liquid petroleum gas which comprises of isobutane and N-propane. So that is being studied and that is being reported. Structural stability is confirmed by the formation energy of -6.178 electron volt per atom, and the dynamic stability by the phonon band spectrum, and the band gap for the phosphoboron is calculated to be 2.734, somehow a wide band gap, so which is also a semiconducting nature. And the structure of phosphoboron band structure along with the pristine phosphoboron is being shown here. The absorption of isobutane and N-propane on phosphoboron. So here the absorption energy of isobutane and N-propane LPG gas is found to be in the range of 0.225 electron volt to -0.774 electron volt, indicating the fission. And the absorption of isobutane on the bridge site is found to be optimum, and for N-propane the top site of the phosphoboron absorbed on the phosphoboron is found to be optimum. And the molecular charge transfer analysis also showed that 0.223 and 0.179 are and 0.043 electron are transferred from the isobutane to various sites. Similarly, 0.126 E, 0.103 E, and 0.07 E are transferred from N-propane to the corresponding sites. And apart from that, electron charge density difference is also being explored how the charge transfer from the base material to the target vapor and vice versa. So the EDD, electron density difference, PDAS, and energy band structure is being reported. Conclusion of this work is phosphoborane was found to be dynamically stable, and the presence of absence and the absence of imaginary frequency in the phonon band spectrum infers the dynamic stability. Band gap is 2.73 electron volt, and electronic states near the Fermi level were dominated by the p orbitals of boron and phosphorus atom in the phosphoborane. And the next work is with regard to the novel square octagon antimony phosphate. So here we used the allotrope of square octagon and antimony phosphate nanosheet. So group 5A and 5A nanosheet is being used for the absorption of some of the polycyclic aromatic hydrocarbon. So that this is a Hecklite structure of a square octagon antimony phosphate SOSBP nanosheet that is being investigated, and the SOSBP nanosheet is structurally stable, and the semiconducting nature is found to be, the band gap is found to be 2.26 electron volt, and here the polycyclic aromatic compound hydrocarbon, polycyclic aromatic hydrocarbon PAH molecules are studied. So which use benzene, anthracene, benzopyrene, and benzofluoroethene. So that is being studied. So band gap, PDAS spectrum, and absorption energy, charge transfer, energy gap, average relative energy gap. Concluding remarks: so that SOSBB is structurally stable and it is used as a base material for PAH, and the results show that SOSBP nanostructure is a promising material for sensing a benzoanthracene, benzopyrene, and benzofluoroethene in the atmosphere. And the last work that is being discussed today is the absorption property of a polycyclic aromatic hydrocarbon reported in inorganic chemistry communication. And here we used a beta allotrope of antimony nanosheet, antimony group 5A material. And the PAH, the target molecules are fluorine, triphenylene, and pyrene is used as the target molecule, PAH molecules. And here in this work, the new thing is we used the effect of strain on the absorption property of the base material, that is a beta antimony. And work function analysis is also being explored and it is being reported. And here you can see the strain. So biaxial strain, that is a -4% up to 4%. So the absorption energy and work function under strain is also being reported. And the concluding remarks, that is the absorption features, attributes of pH molecules. It causes a reduction in the band gap of beta antimony, and the Mulligan charge analysis also shows a positive charge transfer from pH molecule to the beta antimony sheet. And here the important thing is upon applying the compressive strain, it enhances the sensing response of a beta antimony towards the pH molecules, whereas the tensile strain, it facilitates easier desorption of the pH molecules, which is beneficial for a sensing application. So now my colleague Dr. Nagarajan will continue with some of the designing aspects in the chemical nanosensor. So he will give a demonstration for 20 minutes, and after that we will have some discussion, and we will conclude the session. Thank you. My colleague Dr. Nagarajan will continue with the demonstration. Over to Dr. Nagarajan.
I hope I'm audible. Good afternoon, all. I'm Nagarajan from the Department of Physics, School of EEE, SASTRA, deemed university. So today I'm going to demonstrate how to build a structure, 2D materials, and how it is utilized for many applications, especially today. So we mainly concentrate on GaN sensing applications. So using a QuantumATK software along with the GUI, graphical user interface, virtual nanolab, how to build a 2D structure, then how we are going to exfoliate the 2D material from the bulk material using VNL, then how we are going to make a complex structure, that is base material with the target vapor molecules. So everything that I will show you, demonstrate. So this is an icon, QuantumATK icon here. So that window it will come, right? And here so many options are there. I'm not going to elaborate all these icons. So directly we can go to builder. We can go to builder. So here the software, it have a GUI, that is virtual nanolab. Through virtual nanolab only we are going to build the structure here. And here there are so many options. Of course, that the QuantumATK have a inbuilt structure. So many structures are there in the database. First, I'm going to build the silicon or silicene. The silicon, it is a bulk material. If you're going to exfoliate into 2D material, that we can call it as a silicene or silicane. So just you can go to the builder. I hope the window it is visible to you. Right. So just you can go to the builder here. I go slowly, please follow each steps, or better you can also write. So builder, go to builder, then in add from database. So already there's so many structures where it is saved in the database. Just you can click it. So this window will pop up, and here if you want to get the structure for molecules, so you can choose this one. Crystal, of course, the fullerene, zeolite, so many things are there. Just you can click crystal. So here there's so many structure, it is already saved along with the lattice parameters here. I'm going to select silicon alpha, and here you can see the structural details for silicon in alpha phase. It is belongs to the phase center cubic, and the lattice constant value and space group, what crystal system it is. So everything it is given. You can do double click here, or you can use this icon. The plus icon is there at the bottom right corner. Just you can click so that you can get this structure. It is a unit cell. It is an unit cell. The silicon alpha. It have two silicon atoms. Two silicon atom is there. So anyway, once again we have to check what structure it is. Just you can go to the bulk tool in the right side. There's so many options are there. Go to the bulk tools, and here the lattice parameter. So initially, whatever the sample material that we are going to build, you're supposed to check the lattice parameter here. Just you can click. Yeah, of course, it is a phase center cubic. This is the lattice constant value. Here it is displayed. Yes. Next, with this unit cell, we are not going to do anything. So we have to do a super build. So that option also there. See here in the bulk tool itself, the repeat option. The repeat option is there. Just you can click. And here, of course, in the lattice parameter, the cubic means that you know very well A that is equal to B equal to C, right? So in that way only you're supposed to super build here, that option. If you are giving 3 or 2 or 3 here, so you're supposed to put the same number for all, so that the structural details will not change, right? So here I'm going to super build with this number 3 cross 3 cross 3. Just I applied. So we are getting this, the bulk silicon material. So just you can rotate in all the direction, and better you can keep the orientation like this. So how we can get a 2D silicon material from this bulk material? It's very simple. Just you can keep the structure in this orientation. There are so many 3 layers are there. So just you can cut or eliminate the unwanted layer. Just you can select all the atoms. Just click delete button, so that we can get a 2D silicon material. Yes. So immediately, so now we got the 2D silicon. You can say it is silicene. Silicon, it is in the bulk material. If it is come to 2D, is supposed to named as a silicene, right? So better you can keep all this layer, the single layer, it should be kept at the center of this periodic boundary condition, right? So that option also there. Just you can go to the coordinate tools, and here the center option is there. Since no one of the atoms should go outside the box, so outside the boundary. So for that, in order to ensure, better you have to use this center option, the coordinate tools. Just you can apply this so that all the atoms where it is retained inside the boundary of simple face center cubic box. Yes. So this is silicene. As I told, how we are going to the passivation of the hydrogen or halogen atom, right? So here directly you can passivate the hydrogen atom with this option. You can see, just you see the cursor, I go to this icon. So using this icon, you can passivate with hydrogen here in this silicene sheet. Just you can click this. So automatically say that the hydrogen atom where it is passivated over the sheets, right? So why we supposed to go for passivation? Some dangling bond is there while you are going to exfoliate the 2D material. Some dangling bond, it may be formed. So in order to eliminate that, the dangling bond, we must passivate with the hydrogen or halogen atom. In this way you can do. Since how, in what way we are going to passivate the hydrogen atom, so that we can name the sheet, the silicene 2D sheet, in the way of silicane or silicene. So this atoms where it is exactly passivated in ups and down, it is exactly perpendicular to the sheet. So I can call it as this is silicane. This structure name you can call it as a silicane. If you are going to passivate the atoms, the hydrogen atom at the terminated end, I will show you. So if your passivation of hydrogen atom at the terminated end here, this material you can call it as a silicene. So in what way we are going to passivate with the hydrogen or halogen atom so that the structural name it will be differ. Yes. Now I will show you what are the initially we supposed to ensure that the material it is stable or not. So using the cohesive formation energy, as I told, you can use the cohesive formation energy as well as the phonon band spectrum. You can confirm the stability of that material. Only after that, the remaining, the analysis that you are going to do. Yes. So how we are going to run our analysis? So now I am going to analyze the structural stability as well as the electronic properties of silicane material. This is our material. So I'll show you how to analyze this. So after we build the structure, this is a 2D, the silicane structure. Just you can you just follow that a cursor. Where I go to, just I minimize it. Here the bottom right corner. So just you can click this and go to the script generator. Script generator. Yes. So this window will come. So only here you are going to write a script for the given base material. And here the different types of calculators there, LCO calculator, a plane wave, semi-empirical calculator, a force field calculator. So many calculators are there. So now today we are going to choose LCO calculator. So whatever the option we have, just you can double click here so that will come to this window. Right, this is a script window. So whatever the calculator and whatever the option that we record here, just you can double click so that it will come here. Then you can again double click the LCO calculator. And here you can choose what basis set and what are the exchange correlation function you are going to use. By default, the exchange correlation function GGA PB, it is there. Since the selection of GGA and PB, it is underestimate the energy as well as the band structure, so that we can go with some meta GGA or hybrid in order to eliminate the underestimation issues. So we mainly in our work we chosen hybrid GGA and HSC06. Of course, this option it is gives a more accurate result compared to the other exchange correlation function, that level of theory. But today, since it is a demonstration section, I'm going to select a GGA PBE. Of course, if you go for accuracy hybrid, then definitely the computational time it is exponentially increases. So that is one not drawback. So if you want to get the accurate result, we supposed to have that computational time it should be high, right? So today it's a demo section. So I'll choose GGA PBE for fast computing. Anyway, initially we're supposed to optimize the structure. So all the inbuilt structure in the database are optimized one. So I'm not going to optimize it again. So directly I'm going to analyze various properties of that material, structural stability as well as the electronic properties of silicon material. Yes. So these are the accuracy. So while you are going to do the optimization, the tolerance, energy convergence, the tolerance that we are going to fix, and maximum steps, that also the so many options are there. So I'm not going to take elaborately this. So directly I selected GGPB. So LCO calculator I chosen. And then for we are not going to optimize the structure because that the structure it is already optimized. So no need to go for optimization. Directly can go to analysis. And here so many analysis that is there. That option is there. In our work, we mainly concentrate on the absorption behavior of the chosen material for different target vapor molecules. So for that, we need the electronic properties. We need to study the electronic properties of that material. Of course, before we chosen the sample for sensing applications, the structure should have a more stable as well as it is belongs to the semiconducting property, semiconducting nature. So that semiconductor material only it is of choice for studying the sensing of various target vapor molecules. So for that I'm chosen the band structure initially. So first we need to check the band structure. That is from the band structure you can get the band gap value. The band gap value of the proposed structure. And here you can choose a brilliant zone root. That is a high symmetry point of the respective crystal structure. So for a phase center cubic crystal, these are the brilliant zone root. That is a high symmetry point. So here I take gamma XWL gamma. That is, these are the symmetry point for the space center cubic structure. Just right click. And for sensing property, we need the electron difference density, EDD. As I told, EDD, electron difference density. Then I go with the Mulliken population analysis. So through the Mulliken population analysis, you can get the charge transfer values. The how much charge, what about the magnitude of charge where it is transfer among the base material and the target vapor molecules that we can study with the support of the Mulliken population. Then the projected density of states. The projected density of states here. Band structure and the PDAS, so both it is used for studying the electronic properties, especially in the projected density of state, the which particular orbital where it is mainly influenced the total density of states. So that we can easily study with the support of the PDAS. So how that the orbital overlapping among the different orbital that we can also study using the PDAS spectrum. So here the projection I chosen the elements and cells since I want to know which particular orbitals SRP or d orbital where it is hybridization or overlapping with the target vapor molecules. So for that I have chosen the projection into the elements and cells, and here also I taken the range. I changed the range, energy range from -4 to +4 here. Only two changes I make here. Just we click OK, and directly can go to the total energy. So total energy is very important. Whatever the structure, whatever the application that you are going to do and simulate the structure, the total energy is very important. So only through the total energy you can get the formation energy as well as the absorption energy of the molecule, of the complex structures. Yes. So for our work, these 5 analysis is far enough. Further, if you want to go with the dynamic stability, you want to study the dynamic stability. So for that, we have to choose the force field calculator. Only through the force field calculator, some of the option is there. But in LCF calculator, we can't do the phonon band spectrum. But in force field calculator, you can do the phonon band spectrum. So through the phonon band spectrum, we can study the dynamic stability of the structure. Anyway, first initially we have to confirm the structure stability with the support of the cohesive formation energy. So for that we need the total energy here. Yes. So after that you can just name it. For this we have chosen silicon, right? Silicane. So in quantum ATK, actually, if you are not having VNL, we are supposed to write the script in Python program using Python. Yeah, of course, the script it is written in the Python program, but everything is that will take care by the VNL, the virtual nano. It's like the document writer. The main document writer is VNL here. Just we have whatever what are the analysis that we are going to do. Just we can choose that one. So VNL will take care. So that's why that script generator is there. Whatever the analysis or calculator, just you can keep all those things in the script window. So the VNL will take care. That will write the Python program. That is input file that will create. Again, see, once we have the selected all the calculator and the analysis, just you can go to the bottom right corner here. Next, where you supposed to go? So it will be bold. See jobs. Once we created the script generator, directly can go to or submit the job here. Yes. So where we are going to save here? Just you can create a separate folder. So here I give the today's date. And here I separately make a folder. And here I am going to run. Yes. And here there are so many options are there, multi-process, parallel, thread parallel, serial. There's so many options are there. You can select any one. So I am chosen the thread parallel single process. Just you can click add. So once you add, immediately it will not run. So just you can click we have submitted the silicon job here, and here the status pending. So we are going to initiate. In here the play icon is there, right? Just you can click. So now that the job is running, so it will take less than a minute, since we have taken only 25 or 24 atoms only. And also we have chosen a GGA-PB exchange correlation function. So the computational cost is not much. It will not take that much. So within a minute, it will complete. Yeah, so see that the total time it takes only the 19.12 seconds. So job is completed, and the tick, the symbol it will come. Yes, which means the job is completed successfully. Now directly you can go to the main window. Directly you can go to the main window here. So the data, here you can check your job. Already we are submitted here only. So go to our folder, silicon. Yeah, this is this one. Yes. Just we can click this folder. So we got the output of what we have selected. Band structure, we got electron difference density, molecular population, projected density of states, and total energy. So how we are going to view the output? So the total energy, of course, here the text representation, since we have only the values. So for that, the total energy as well as the molecular charge, we have to select this text representation. Just you can click this, we can get this value. Total energy of the pristine, the base material, we are getting this minus 2352.75 we got. And for molecular populations also the test representation, the respect to the element and the charges where it here it is displayed. So you can get the molecular charge. The molecular charge also we can get. And for band structure, electron difference density, projected density of states, so we need the pictorial representations. So for that, just you can click the band structure. And here one option is there. So using this option, you can get the schematic diagram of the band structure. So just we can click this, we can get a band structure. Since we have chosen the high symmetry point gamma x WL gamma. So the band gap is that you know very well, the difference between the conduction band minima and valence band maxima. So we are getting this, that value also here it is displayed, the direct band gap it is 2.249, yes, and here the indirect band gap is 2.1312. So how we can know about this, the band structure where it is a direct or indirect band gap semiconductor. Yeah. So here both valence band minima and conduction band minima and valence band maxima, it is in phase. Actually, we have to choose the high symmetry point gamma. Only we have to choose the high, that is a reference point in order to find out the band gap here, right? So if the both the conduction band minima and valence band maxima were in phase, so it has same k vector, then you can say it is a direct band gap semiconductor. If it is not like that, then you can say it is an indirect band gap semiconductor. Yes. So for that, our material is belongs to, of course, the semiconductor. Since the band gap is around 2.24 or 25 electron volt, we got. Yes. So here you can, I will show you. You can change the scale also. You can change the scale. S3 to S3 I want. So we can get a clear view of the band structure here. Then you can find what type of the band gap it is, direct or indirect band gap semiconductor, right? Yes. So next, the PDAS, how we are going to view the PDAS, that also I'll show you. So PDAS, here also we need the pictorial representation. So for that you have to choose this icon for get the PDAS spectrum. Yes. Yeah, so we got the PDAS spectrum here. And here hydrogen, of course, L equal to 0 means, see here, the L equal to 0 means it is a s orbital, H s orbital. L equal to 1, it is P. Anyway, the H it have only one S, right? So H that is equal to H, s orbital we need. And for silicon, if you don't know about this orbital, you have to Google it. What is the electronic configuration of the particular element? So for that, you come to know what are the elements, orbital that we need, right? So for silicon, S and P orbital is enough. You can also change the color. So for that, the silicon L equal to 0, that is s orbital, I have selected the red color. And for L equal to 1, it is P, I have selected blue color. And for hydrogen, I select red color. So in this way, you can select. The pattern of the graph also you can change. It is in line. You can also choose the stacked one and also filled. So there are so many options for there to visualize the PDA spectrum here, right? So in that band structure, I taken the scale range from -3 to +3. Here also I can take 3 to 3. So why I'm choosing the same scale, I'll show you. Yes. So in order to compare the band structure along with the PDA spectrum, this way you can do. This way you can do. Yes. So now we got a band structure along with the PDA spectrum. Of course, it is belongs to the semiconductor. See that the hybridization, orbital hybridization of the silicon S and the silicon p orbital, it is found to be more in the conduction band here, right? In the conduction band when compared to the valence band. Yes. In this way, you can interpret the total dust, which particular element orbital where it is contributing more to the total dust, that you can easily find using the projected density of states. Right. And then for electron difference density, so the electron difference density here also you can go with a viewer. Of course, the isosurface that we are going to choose, right? So you can also change the orientation of that material. So why we mainly taken the electron difference density? So for that we come to know in which particular sites or the place where the electron accumulation as well as the electron deficient where it is happened. So that we can easily find out through the electron difference density. Yes. So here the graphical property, that option is there. Just you can go. I don't want that the box. Just you can take it out. Then the isosurface, based on the isosurface, right? The electron difference density. So that will be showing clearly. So now I am chosen 0.5 for this, the ISO value. Of course, you have to go with a trial and error method in order to get a proper isosurface value. Isosurface values. 0.05, we can try with the 0.05. Yeah, it will be good compared to the previous one. And of course, the opacity I chosen 0.5 for all. And here the color map, different color map also there. So better you can select the blue, red, or that is your wish. You can choose any one of the color here. Of course, in order to differentiate the electron excess and electron deficient, I have to go with a plus or minus ISO value. Then only the different color it will show here. So there and here it shows that the red color region. You can see the red color region. It is represent the electron excess. The accumulation of electron is there in the red color region, and for blue color, so there the electron deficient it is happened. So here from here itself, you know the electron where the excess it is found, only there the target molecule can easily absorb. So based on that, you can select the what is that? A different absorption sites that you can decide. So here you can see that the top, the hydrogen especially, and the hydrogen atoms at the red color, that is found. Notice that. So the electron excess is there. Further, the target molecule where it is adsorbed over here, it is a favorable one. It may be a favorable one. In this way, you can decide. Of course, in this, the bridge type, the bridge site among the silicon atom, the red color region is there, right? It is, you can call it as a bridge site. So bridge site also it is favorable one since the electron excess is there in the bridge site. So based on that, the color gradient, the red color, the electron excess, wherever the electron excess is there, there is a more probability to absorb the target molecule on the particular sites. Right. Okay, so these are the way, I think these are the parameters that we record in order to sense the target vapor molecules. So only here we analyzed for base material. Next, how to make a complex structure, that is base material along with the target molecules, that I will show you. So this is a base material. Of course, I think we are taken from the database. We have taken this structure from the database of QuantumATK. In another way also, you can build the structure. Since we mainly focused on a group 5 material, that is phosphorus, arsenic, antimony, etc. So how to build the structure, the phosphorine or arsenine or antimony? So that I'll show you. I think that structure, it is not there in the database. So once you know the crystal structure, lattice parameter, VOC position, you can easily build the structure. So that option is also there in the builder, that I will show you. Yes. So here you can go to builder again, add, then here the separately the plugin add-on option is there. So through add-on option, you can plug in the crystal builder. Crystal builder option is there, right? Okay, so just to go to the build. Database means the saved structure that we can get it from the database. If you want to build your structure, so that you know all the crystal details, including the VOC position, then you can go with this option, crystal builder. So it will come like that. The crystal builder window will come. So initially we record the space group, then the lattice constant value, then after that the VOC position of the particular element. So for that I will show you already the reported value, already the reported work is there, that I will show you. Yes. So it is already reported by one of the researchers. So all the details about the phosphorine of various allotropes, here it is given in the supplementary information. So here you can see the phosphorine material, the blue phosphorine, or you can call it as a beta phosphorine, or you can call it as a chair. The space group value it is given, and also the lattice constant information. Mainly the VOC position is very important. In order to build the structure through the crystal structure add-on, so we need this VOC position, right? So using this detail, how we can build the structure, I'll show you. Yeah, so here the crystal builder, just you can take. First, initially, I'm going to build a blue phosphorine or beta phosphorine or chair phosphorine, and space group along with the number, the respective number it is given 174. So directly can go to this. Select P3 bar M1. Yeah, it is exactly matched with that 164. And next we need to give the proper lattice constant value. It is already reported one optimized structure, optimized lattice constant value. Here it is given. So directly you can take 3.269, and for C 25 you can give, right? Then we need the VOC position for P1, phosphorus first atom. Just you can click, and the so many options are there, right? So many options there. If you are not having that much knowledge about this, directly can go to XYZ here, and you can give the number like this: 0.667, 0.33, or 0.524. So like that you can give. So for this, just you can see that the 0.667, 0.33 is nothing but 2 by 3, 1 by 3 here. So directly you can choose this. And in Z, you have to give the number manually. You just type the number manually, 0.524. So now we give the VOC position for phosphorus atom. But here in default, by default, the element it is hydrogen. Just you can click, do double click. So you can change the element here. You can change the element phosphorus. Phosphorus, yes. So this is phosphorus, first atom here, and Vico position of this value also it is given. Space group it is chosen, lattice constant value also it is given. If you are having these details, you can easily build a structure. Just you can click the build option here, you can get this way. So directly we are getting the unit cell of phosphorine, blue phosphorine or beta phosphorine material. Yes. Then how we can make a sheet? So we have to go with a super build, right? Of course, once you get this, the material, we need to check this material is belongs to what. So for that, you go to the bulk tool, go to the lattice parameter here. Of course, the lattice type is hexagonal, and the lattice constant it is given by us. So 3.269 and here 25. Right. So now we can directly go with the super build. See, while you are doing this, the repeat option. So one thing you're supposed to remember in the lattice parameter. So where we gave big number, it is 25, right? So A that is equal to B, but not equal to C. That is a hexagonal structure, right? So in C we gave a big number. It is comparatively this. It is a 25. There you should not repeat the structure. Right. Anyway, I'll show you. In the repeat option, A that is equal to B. So you must give whatever the number it is given here. The same number is supposed to give it to here for B. And C here, it is a big number 25. You should not repeat. So just you can keep the C value that is equal to 1, then apply. So directly we can get this beta phosphorine, or you can call it as a blue phosphorine or chair phosphorine. So it is a buckled in structure. You can see in the side view, it is in the buckled in structure, and due to the sp3 hybridization. Whereas in the case of graphene, a flat, the plain sheet we are getting, that's why it gives a zero band gap. So here, due to the sp3 hybridization, the buckled structure it is formed. So finally, we are getting the semiconductor nature of that material, the band gap. It is easily get open on because of the sp3 hybridization here. Yes. So why, if you are giving any number in C, I'll show you. If any number, if you are giving in C, see we are getting like this. Anyway, we are going to eliminate the remaining unwanted layer, right? Okay, so that's why I told you, no need to give any number if the particular lattice parameter value have big number. Yes, so there you have to give one, no need to repeat anyway. So we are having phosphorine, beta phosphorine nanosheet. And here how we are going to incorporate or place the target molecule over the sheet, so that we can see. I'll show you. So before that, what are the possible sites are available here in the buckled structure? In the buckled structure that we can see. So one of the sites you can say this top. So you can say this is a top site. I'll show you. This is a top site. If you keep the sheet like this is a top. And I selected the atom at the bottom, right? The lower layer, you can call it as a valley. You can call it as a valley site, right? And in between these two, right? I just you see the cursor. So this site you can call it as a bridge site. You can call it as a bridge site. Here also you can bring the molecule. And the cursor where I pointed out, that is a ring site, or you can call it as a hollow sites. Ring or hollow sites. So that is, so initially, of course, we have to go with a trial and error method. You have to bring the molecule to all the possible sites and optimize, or you have to run from the absorption energy. From the absorption energy, you can find out the most possible. That is a global minima sites. You can call it as a global minima sites. So which particular sites have give a least energy, the lowest energy value, so that you can call it as a global minima sites or a highly stable sites. You can call it as a highly stable sites. That particular sites only we are going to concentrate in the further discussion. Right. And the remaining the higher energy sites that you can omit, eliminate. Yes. So now I'll show you how to bring the molecule here, how to make the complex structure using this. Anyway, I'm not going to run. So the similar thing only in the silicon, what we are going to analyze, the band structure, PDOS, the same, the parameter that only that we are going to do here. So it will take more time. So just I'll show you how to bring the molecule and how to place the molecule over the particular sites. I'll show you. So for that I will take through builder. Of course, in database so many molecules are there. I choose the molecules here. The molecule option is here. And just I take ammonia molecule I'll take. Yeah, just you can click this ammonia molecule to come. So the main advantage of studying DFT here, yes, you can go up to the atomistic level. So this we cannot do anything in the experimentally, right? In the computational, in DFT, using the quantum ATK, we can go up to the atomistic level, in which particular the size the molecules where it is adsorbed strongly or weakly, so that which particular adsorption sites where it is favorable. So everything that we can easily find in the atomistic level. That is one of the advantage of using this tool. Right. So we have ammonia here and also the beta phosphorine nanosheet is here. So how to make a complex structure, I will show you. Just you keep the sheet, and here ammonia, just to see the cursor, just to click the ammonia, just to drag the molecule slowly and drop it here. Yes. So the ammonia, the molecule where it is here, here that icon is there, right? All the four direction that the arrow mark is there. Just you can click it so that the all the options where it is enabled here. If it is click, no one of the options were enabled. Clear? Just you can click it so that all the options were enabled here. Right. So initially our aim is we supposed to bring the ammonia atom inside the boundary, inside the box, hexagonal box. So from top view as well as the side view, you have to bring the atom, that is molecule. Okay, so side view as well as the top view. Of course, now we bring the ammonia molecule inside the box. Next, how you are going to move or place the molecule over the particular adsorption sites, that I'll show you. So before that, actually, so we're supposed to do the frequency analysis, but that option is there in the Gaussian. But here anyway, at present, I will not show you that using the Gaussian that we can find out so which the symmetry, that is a stretching mode that we can easily find through the vibrational analysis. So based on that, the particular atom that we can bring to the particular adsorption sites here. So now we already performed a number of times of ammonia. So the nitrogen atom shows highly reactive. So just I'll make the ammonia atom, it should be directed towards the sheets. So for that, I'm going to rotate this molecule towards the sheets. So that rotate option also there. Just you select the ammonia molecules alone. Don't select all. Just you have to select the ammonia molecules alone. Since we are going to rotate the ammonia molecule only, in this way you can select, or easiest way, just you can bring the cursor to any one of the atom and double click so that it will select, right? And then the rotation option is there in the coordinate tool. Rotate option is here. Through which direction you are going to rotate. So here it is there. So initially you can go with a lower number so that which direction it is rotating, we will know. Okay, I think this is enough. Right. Since the nitrogen atoms where it is down, so that you can refer the nitrogen atom here. So based on the nitrogen atom, right? You just to refer the nitrogen atom and bring the molecule to the respective sites. So in order to choose the adsorption sites, you're supposed to oriented. The top view is a perfect one. So from the top view only can select the respective adsorption sites. And here I am chosen, see, just you click one of the atom and you can drag the molecule wherever you want, right? Just I keep the molecule here. So this sites from the top you can call it as ring sites or hollow sites, right? This is ring sites. Then you can bring this molecule. Of course, you have to refer the nitrogen atom. The nitrogen atom, it should be over the particular sites. And here I'm showing you, this is the top site, right? And then I bring the nitrogen atom to the valley sites. This is valley sites. Then you can bring the atom, nitrogen atom. It should be pointed out. So where I place it now, it is a bridge site. So there are so many sites out there. In this way, you have to bring the molecule. Okay, so from the top view, you can choose the sites, right? Adsorption sites. But what distance it should be there in between the sheets and the molecule? What about the optimized distance? So that you are going to optimize only. And before you are going to optimize, you just to go to the side view. You just to go to the side view. From the side view only you can decide the distance between the sheets and the molecules. So just you can zoom option also there. Just you drag the molecule vertically so that the sides will not change. Just you can go slowly, slowly until the bond formation takes place. Until the bond formation takes place. Yeah, now it is bond formation takes place. Just you can lift the molecule a little bit upward direction. Yes. Okay, this is fine now. So this is again you have to check the sites where we placed, where we chosen ring sites or hollow sites. In the side view also the bond formation is not there. If the permanent bond, if it is formed, then the molecule definitely it is chemisorbed over the graphene. So our ultimate aim here for sensing applications, the molecule must be physisorbed over the proposed material, right? So now you are going to optimize the complex structure. Then you have to analyze whatever the analysis that we already made before, right? Find the total energy, then band structure, PDAS, then EDD, then ELF also. Whatever the analysis that we want, we can do. Yes, that it is related to the sensing applications, right? Okay, so here mainly band structure that we calculated, right? So electronic properties. Sir, the Professor Chandiramouli sir showed the tabulation. From the tabulation that you know, the important parameters, it is displayed there. The first one is adsorption energy. Of course, through this total energy, you can find out the adsorption energy. So based on the adsorption energy range, you can conclude whether it is the molecules were adsorbed, physisorbed or chemisorbed, that you can decide. Yes. Then the molecular charge transfer, the magnitude, how much charge where it is transferred among the base metal and the gas molecules. So based on that, the polarity of the molecular charge, you can say the direction of charge transfer. That also it is important parameters for studying sensing applications. Then after that, the band gap, that is very important. The band gap variation is very important. So initially we got the band gap, it is around 2.2, right? Then after the molecule get adsorbed over the sheets, definitely the properties get changed. Some of the electrons, the charge transfer takes place. Okay, so on because or some of the internal strain it will be happen over the material. So due to that due to the many factors, definitely the electronic properties of that material, especially the band gap, gets changed. So that variation of band gap we are going to notice, right? So how much that band gap it is differ. So based on that, the sensing properties of the material towards the target vapor molecule we can study, right? So we are going to study only the variation of the electronic properties upon the absorption of the target vapor molecules on the proposed sample. So based on that, the variation of band gap, that value, you can say which particular the absorption sites, the molecules were absorbed strongly or weakly. So based on that value, you can easily find. Yes. So similarly for each molecule, some other molecule also that you can take a different target molecule also you can take and just allow the molecule to absorb over these sheets. Then you can get the selectivity. So which only the particular gas molecules were absorbed, that variation of electronic properties it is high, right? So which particular the molecule where it is absorbed over the sheet, so that the variation of electronic properties is found to be more, that is a selectivity. So the base metal where it is strongly, you can say that it is a suitable material for sensing that particular vapor molecules. Yes. Okay, so here I stop the demo section here. So I hand over to Professor Chandiramouli sir. Any query is there, you please ask. Yes.
But all any
Now
other
this session
discussion?
is now this session is open for the Q&A. So if anyone have any query, they can directly ask Vidhi sir. So if anyone has any query, they can let us know. And if there is no query, I think we need to conclude this session. Sir, please try to have a look on the chat box.
The PPT will be shared by IMS.
Yes, of course, the absorption energy difference, the absorption energy of complex and the base material, of course, molecules, that we can get the absorption energy. We are not showing any formula here, the expression. The difference.
The formula you can find from the like a QuantumATK documentation site.
Yes, yes.
That is already available.
Everything
Yes.
is available there. Yes. Okay.
Yes. Yeah, we'll share the recording and also the PPT after this session.
I hope no other queries are there, so that we will conclude it, sir.
Yes. So as we come to the close of this insightful session, so I would like to extend my gratitude to both our esteemed speaker for their valuable contribution. So first and foremost, a sincere thank you to Dr. Chandiramouli for sharing his profound research insight on the gas sensing application of the monolayer materials by the QuantumATK software. So your presentation provided us with a deep understanding of how atomistic simulation are transferring the landscape of the nanoscale material research. And I would also like to thank Dr. V. Nagarajan for the excellent live demonstration. So your practical walkthrough of the QuantumATK platform greatly enhance our comprehension of the tools and technique discussed, and also offer a valuable hands-on perspective. So together, your combined expertise has made this session of the Faculty Interaction Webinar Series both enriching and inspiring. And I would also like to thank all the participants. Also, your presence and thoughtful interaction made the session truly enriching. So we hope these insightful share today's inspire new ideas and collaboration in your journey, in your research journey. Yeah, thank you so much.
I thank all of you for attending the webinar. Also, I thank IMS and Mr. Deepak Upadhyaya for arranging this webinar. Thank you all.
Thank you all.
So once again, thank you so much. Thank you.